Okay guys, this is the second video of position and positional controls, and again this is a big chapter, and again I'm not going to even try to get through all the variations and ways we can manipulate this system to control. What I really want to focus on is just sort of the fundamentals of position, and the fundamentals of position rely on at least some fundamental understanding of datums and the tolerance zone and basic dimension and all those things. They come into play very strongly with position. So what I'm going to do here is I want to have you go back to figure 7.2. Now in the previous video we used figure 7.2 and it's a great example of a partially constrained part and how we can use the datums to constrain it just enough to validate these positional dimensions for these small, what are they, 3 millimeter holes in this ring. But it is a busy drawing. You have all the location dimensions that are basic. Even though they don't have a box around them, the default note tells you that they are basic. So you've got all kinds of dimensions and the part itself and the ID and the OD and the thickness and all of that stuff. So what I wanted to do was strip away some of that stuff and really strip away the part and all the features and focus on the datums and on the basic dimensions, because this really is sort of at the heart of GD&T, is the notion that we can define perfect geometry, and we do that with the basic dimensions. And then once we have that perfect geometry established with the basic dimensions, we can use those locations to hang a tolerance zone. And a tolerance zone obviously can be as big or small or round or square or whatever we want to do. That's the idea of GD&T, is that we have complete control of it. But in this instance, we have a cylindrical tolerance zone. It's defined as a diameter 0.3, so 0.3 millimeter tolerance zone. Again, I want you to always remember that when we're talking about the tolerance zone, we are not talking about the feature. Okay, if these were square holes in this ring, you could just as easily have a cylindrical tolerance zone. It is the boundary within which the axis of the feature, the derived median element of that feature, has to reside. So it is the shape of the tolerance zone, not the shape of the feature. We would have exactly the same feature control frame if these were triangular holes, square holes, round holes, elliptical holes. Doesn't matter. We are controlling and defining a zone that is cylindrical. And with those holes stripped away here, I hope it's a little bit easier to see that what we are defining on this ring are cylindrical tolerance zones. And once we have this perfect geometry established, now again I don't have all the dimensions there, but each one of these locations is located per figure 7.2, and those are perfect locations. They have no tolerance. The tolerance is going to be established by the tolerance zone. So around each one of these 1, 2, 3, 4, 5, 6 locations, we are going to have a tolerance zone that is 0.3 in diameter. Now again, 0.3 in diameter is 3/10 of a diameter, or 3/10 of a millimeter. That would be 12, 13 thousandths in diameter. So this is a very small cylinder that is being drawn around this location. Obviously I can't even draw it that small. Okay, so there is a cylinder that is centered on the location established by the basic dimensions, and that cylinder is 0.3 millimeters in diameter, and the length of that cylinder is the length of the part. So I've drawn that tolerance zone, or each one of these 6 tolerance zones, each one of them is the same, and put in each one of these locations. It is 0.3 in diameter, and it is 12 millimeters to 10 millimeters long. Well, how long is it? It depends. It depends on what the length or the thickness of that part is. The tolerance zone is as big as we define it. We define it as 0.3 in diameter, and it's as long as the feature is. So if we make one of these rings that is 12 millimeters thick, that's about a ½ inch, and so that's pretty close. That tolerance zone would be 12 millimeters long. If the next ring we make, we face it off a little bit short and we end up with 10 millimeters, then the tolerance zone is 10 millimeters long. That is the default. It is as long as the feature itself. So that length is variable, and it depends on the actual length of the actual part. All right, so once you have that notion of this sort of a see-through cylindrical tube stuck at each one of these locations, we now can sort of visualize what can go on within that tolerance zone. Again, this is blown up huge compared to that actual cylinder. That actual cylinder is very, very small. So it looks like a lot of error can be accumulated in this tolerance zone. It really can't. It's a small cylinder. But what can happen? What can we accept as long as it fits within that tolerance zone? Okay, so we don't have any other controls here. We don't have any flatness, we don't have any orientation, we don't have any other control but the positional control. That positional control puts this cylinder at each one of these locations, and once that cylinder is up there, we have to accept whatever fits within that cylinder. It's kind of like, you know, a supermarket sweep sort of thing. You get a basket, whatever you can fit in that basket, you get half price off. Same thing applies here. Whatever fits within the cylinder is by definition acceptable. Okay, so now let's look at those potential errors that we can see. And even though it is intended as a control to control strictly the translation of this axis anywhere, and it does do that. So let's look at that set of errors that we could possibly have. Now, ideally, the engineer is hoping that that axis of that actual drilled hole will be right in the center of that tolerance zone. That is the perfect location. That's exactly where he wants them, but he's not likely to get them there every time. So if we look at just the translational error that can occur, that if the part moves a little bit in the fixture, if it's loose in the fixture, for instance, that could put the next center line right here. Could put it anywhere in this cylinder. All it's doing is moving around, and eventually, if it gets bad enough, it gets loose enough, it's going to bang into the walls of this cylinder. And that's okay. We can take it right out to the edge or the periphery of that tolerance zone, and that'll be an acceptable part. Now, if the next part is, a 1/1000th of an inch outside that tolerance zone, theoretically that is a rejected part. You are outside the tolerance zone. So you've got 0.3 millimeters running room, and if you put your holes in nice and square, they can move around a little bit on that surface within that tolerance zone. That's the translational part of it, and that is really what position is intended to control. Okay, but we don't have any other controls, so it's that tolerance zone for position has to take care of all the other aspects of those features, everything else that can go wrong. So what else can go wrong? We visualize the hole going in absolutely perpendicular to surface A, which is the bottom of this ring. We would like those holes to be exactly perfect, but that tolerance zone will allow some orientation error. We might end up with a little chip underneath the ring and drill it off at an angle. So that tolerance zone will allow me to put in a tipped hole. And it can be tipped as badly as touching the tolerance zone here at the top and touching the opposite side on the bottom, or anything in between. Anything else goes for orientation. So in this instance, the tolerance zone is controlling the translation and the orientation. And again, since there's nothing else to tell me otherwise, I also have a form issue with the hole. Now, what can go wrong with the hole? The hole is intended to be a 3.32 millimeter diameter cylinder, and so it should be cylindrical. But there's no cylindricity control, so that hole could actually be tapered in that fashion. It could be a conical hole. It could be a curved hole. As long as the center line of that feature fits within that tolerance zone. I didn't do that very well, did I? That hole can be, let's say, bent or not straight because there is no straightness control. The tolerance zone for the orientation or the position has to take care of that. So again, that's why we have the additional tools, is that we may want to control the translation to some size of tolerance, and we may be able to allow a larger tolerance for straightness or orientation. And if we do that, if we want to do that, we have to create another feature control frame with another tolerance zone and take care of that specific aspect separately. But again, if you don't do that, everything fits into that tolerance zone, and any amount of lack of straightness, lack of cylindricity, lack of roundness of the hole could be oval shaped. Kind of like when you drill a hole in sheet metal, it's very seldom a real round hole. All of those errors are going to be acceptable as long as the amount of error doesn't exceed the boundary of that orange cylindrical tolerance zone. Okay, so again, this is sort of review, I guess, or elaboration on the fundamental aspect of the tolerance zone. Okay, now in the previous video I mentioned that the constraints caused by the datum. The datums are there to constrain the part and establish the relationship of the part to the features that we're trying to control. Okay, so here's my ring again, and I said that I have datum A, which is a plane. And the rule of datums is that I have to, if I establish a surface as a datum, I have to stay in contact with that datum plane. Okay, so how do you do that in reality? Well, you set the part on a machine table, or you set it on a vise, or you set it on some reference surface, and you can't have it tipped, and you can't have a chip underneath it or a burr. It has to be in intimate contact with that datum surface A, and then you can start evaluating where the tolerance zones are. Okay, so let's look again at the constraint, the lack of degrees of freedom that each datum establishes. If I am forced to stay in contact with datum plane A, I can translate, I can slide this way and I can slide this way and still stay in contact. So I still have two translational degrees of freedom. I can't translate this way, obviously, because I come off the plane. So I have constrained one translational degree of freedom. Rotationally, I can rotate this way. So that would be yaw. But I can't pitch and I can't roll. So I've constrained 2 degrees of freedom. So not all 6 degrees of freedom are constrained. That means the part is not fully constrained, but doesn't matter. And I'll say no, because if you look at this picture and then you imagine that, once you've established all these positions and you put your part underneath it, get ready to drill it, doesn't matter whether you put that part oriented this way or rotated 90 degrees. As long as it's in the fixture, it's contacting datum A and datum B. It is going to be centralized, and it does not matter. We don't have to constrain it in any rotational sense. And again, that's a little hard, I think, to understand, but that's why this is not a fully constrained part. But what I want you to come away with is the sense that you can look at the part, look at the drawing, and look at the datums, and tell whether that part is fully constrained. If I take a part like this, now this is not a round part, so that if I were to put this part in like this, it would matter whether I mounted it or set it in the fixture this way or set it in the fixture that way. That rotational degree of freedom would be a problem for me on a part of this shape. So in the next example, probably in the next video here, because I'm running out of time, I'm going to show a part like that where I am going to constrain the part fully. I'm going to use 3 datums to control all the degrees of freedom, the rotational and the translational. I'll put it on 3 points for datum A. Datum B, I will force the part to touch 2 points so that now I can't translate this way anymore. I can still translate this way. So if I put 2 points here and 1 point here, I will have fully constrained that part. So I'll use 3 datums to do that. And when I do that, you'll see that I have no rotational degrees of freedom left. In this instance, of course, I had a rotational degree of freedom. I could not roll, I could not pitch, but I could still yaw. If I contact the datum B with 2 points, now I no longer have that rotational degree of freedom. So I have fully constrained the part in rotation and in translation. And for a part of this configuration where I can't allow it to do that in the fixture, I would need that additional datum to constrain the part. Okay, chew on that a little bit. On the next video here, I'm going to talk about figure 7.3, which is a part very much like that. And I want you to look at this, and at this point you should be able to look at this and evaluate each one of the feature control frames. You understand now what the datums do. You understand the material condition modifier, and since in this case we have 2 different features, we have a large hole and 4 smaller holes. They have 2 separate feature control frames because they are separate features, and they are going to have their own tolerance zone applied to them. So look at this video. I will have loaded this, or I think I have loaded this in Canvas, so you should be able to get this. Take a look at it. I'm still struggling a little bit with Canvas and the test, but very soon I should have test number 2 up. I'll give you an adequate period of time to get that one finished. What you will see here very shortly is the election form, or the form that allows you to decide whether you want a letter grade or a pass-fail. Again, you do need to make that election. I do need to know specifically from each one of you which one of those options you're going to elect.